Hi, I'm Gary, and I want to show you how I use Cloudy. Today we're going to look at the continuum file, the SAVE continuum file, and see some ways we can use it with the Veusz plotting program to make publication quality plots. So we're in here in the directory with the M16 model. Let's remind ourselves the saves that we have. Save continuum is the second one. Continuum is a bit of a misnomer because both lines and continuum are in this file. It's going to be saved into this name within double quotes. The spectrum can have any x-axis you like. It can be kilovolts, it can be hertz, it can be microns or angstroms. We're going to select microns, a nice SI unit that is more or less comfortable. There's two iterations in the model. We want to save the last iteration. So this will come out in the file m16.conf. Let's do a pasteboard copy and just look at the file in Excel. Here we go. So column A is the indication of the photon energy of the spectrum. And so we asked for microns. So this is the rock bottom radio. This is down near the plasma frequency of the Earth's ionosphere. And the spectrum continues all the way up to 100 MeV. So it goes across the observable spectrum. This is the incident radiation field. We talked about different components of the radiation field in the RT jargon section. This is the incident radiation field, which we specified as a very simple Planck function. We'll plot that in just a minute. This is the transmitted radiation field, the light that filters through the gas. You'll notice it's all zeros. We're in the rock bottom radio, most likely we're below the plasma frequency for the H plus layer, so that nothing is transmitted through. These continua bins are in UF new units, and they will come out in the same units that you specify in the main input and main output. Diffuse outward radiation field, the net transmitted radiation field. These are these different components we talked about. This is the total reflected radiation field. So that's all the light emitted within 2 pi steradian of the star. The total, the sum of everything. These are reflected lines and outward lines. There are a lot of lines in the spectrum. Column J, there are no lines in this region we're looking at, but there'll be lines other places. And in fact, the line spectrum can be very rich. And it gives an indication of the line ID. It may say carbon 4 or H2O. But in many cases with a rich spectrum, there'll be many lines that overlap in this one continuum bin. So you can't really trust that this line ID is the very single strongest line that's in that bin. There can be many lines in the bin. In line, this column here indicates how many lines are inside this continuum bin. Then the continuum labels, they give more labels. If you see an ionization edge or some feature in the continuum, this should indicate the threshold for individual processes. So this is our con file. Now let's import it into Veusz and make some pretty plots. Okay, we're inside the Veusz interface. Let's see how it is we'll go about making some pretty nice looking plots. So I can go up here to data import and let's browse over. So this is the homework page and we want to look at the con file. So this is it. I'm going to select it. This brings up the data selector. So you need to make sure things are set up. So this is a tab delimited file, which comes across as a CSV file. Here's an image of the top of the file. These are the column titles. And this says that the header row is the first row. So that means Veusz will take this as the header for column 1. Column 3 will be trans. Reflected will be 6. So the rest of this is okay. So we need to tell it that the file is tab delimited. So Veusz has figured this out because you've got nice tabs here. And then finally we go down and I always give the data file, the data columns a prefix, which is the type of save file it came from. So it's a con file. Now hit import. We've imported vector 9200 cells long. So next what we want to do is create a plot. So if we have here a graph with an x and a y-axis, we can see that, but we need to add an xy. So we want to find an xy. Here we go. So this is run a selector for the x data and the y data. For the x data, we want to use the continuum frequency, which is microns in this case. And let's look at the incident radiation field. That should be a black body. So here's our plot. We can't see much because the x-axis is linear, so we just see the far radio. So if we select the x-axis and go here, next we can find the option to make it a log. Okay. Now the problem is there's our black body peaking here. It's a linear scale. We need to change this to a log also. So let's go to the y-axis and find log and select that. Okay, so what have we got here? We've got two black bodies. This is the CMB, and this is the star. This is the wavelength in microns across the bottom. This is hard to read because we have all these dots. We have to select XY, and here we deselect the circles. The circles are gone. Now the line's too faint to be seen. So let's go over here, and it's half a point. Let's make it 1 point. We can splurge, make it 1.5 points. Okay, now the axes are silly. So I'm going to select the x-axis and bring this in and bring this in. The y-axis is really silly. They've got so many orders of magnitude here. So let's bring this in. Here we go, and maybe adjust the x-axis some more clicks. Let's give our plot a title. The x-axis is going to be wavelengths in microns. So Veusz understands LaTeX. So there's microns. And the y-axis can be nu. It'd be something like f sub nu. Here we go. So that's what's powering the cloud. It's the energy coming in. That gigabytes of atomic data is the information that allows you to reprocess this energy into emission from the layer. So what we can do, let's name this incident, and let's look at what is processed from this. So I'll take incident and copy it, and let's look at total. So what we have to do now is change this to total. Okay, let's play with the axes a bit more. The y-axis, there's nothing interesting happening down there. There's nothing interesting happening out at long wavelengths, really. And there's nothing terribly interesting down here. Okay, so what's happened? What's in blue? That's the emission from the cloud. So you can see part of the CMB coming here, and you can see the stellar continuum is peaking up over here. There's another quasi black body. This is the hot dust in the H plus layer. So we have two different compounds and a size distribution. We did not include pause in this calculation. We'll get to those later on. This is not a black body because every grain type has a different temperature, and single photon heating was important. What's happened physically is all the energy. Let's think about what's here. This is the Lyman limit. This is Lyman alpha here, and you can see there's some 2-photon emission. There's the Balmer jump, the Paschen jump, lots and lots of lines. The radio submillimeter will get richer when we go into the molecular cloud. This is a logarithmic scale, so this is an order of magnitude. This is a lot of light. So what's happened is the starlight across this region has been absorbed by the gas. So you can see the Lyman jump here. You can see it's 1.5 orders of magnitude of absorption. So it's nearly all the starlight has been absorbed. You can see here in the FUV that the light around 1,000 angstroms has also been absorbed. So that's just probably dust across the ionized layer. So we have lots of spectral signatures. So what's happened here is this missing starlight has been converted into heating dust and making all these emission lines. So we have lots of plots we can make with this, and you can make these plots look very elegant. This is my preferred way of making plots. There are lots of ways to do it.